Okay, so welcome to today's video. It'll be the first video in our series on similar shapes. Now, you might have an idea of what similar shapes are, but I'm just going to go from the start as if you don't know, well, I won't say not know anything, but not let's just assume we're going to go from the ground up. So whenever we talk about shapes and we say they are similar shapes, what it means is it means that obviously they're similar, but it means they're in a certain ratio with each other. So basically, they're just bigger or smaller versions of the same shape. So for example, I have drawn a triangle here and the side lengths are 3, 4, and 5. So if I have a similar shape would, let's say, have these side lengths of 6, 8, and 10. And you might say, but how do I know they're similar? Well, the reason is because there's a certain scale or a ratio with which it increases, and every single length is increased by that same ratio. So if in this case it's 2, so basically I'm saying 3 times 2 is 6, and this is the one corresponding side, so I color coded them. And then 4 times 2 is 8, and then 5 times 2 is 10. So these two shapes are similar because they are in the same ratio to one another. If this was maybe an 11, you'd say, well, the 3 times 2 is 6 and the 4 times 2 is 8, but 5 times 2 is 11. Well, sorry, not 11. So this means these two shapes will then not be similar. So it's not a very difficult concept, just means that they are in relation to each other. Now, there's certain deductions we can make or little tricks we can do when we work with this. So the first one is when we compare, well, before I get into that, the side lengths, obviously they have a certain ratio. Like I said, we multiply them by a certain number. But something different we can also see is that the angles in similar shapes would always be the same. Now I know this one is 90 degrees because this is a 3, 4, 5 triangle, so because of Pythagoras, but I'd see that this angle has to be or will be the same as that angle, and this angle will be the same as that angle. So all angles or corresponding angles in similar shapes will also always be equal. So alternatively, if I had to make this 11, then suddenly that would change that angle and the angles will no longer be the same. So similar shapes can, obviously I've drawn a triangle, well, some triangles here. All squares are obviously similar shape, if you think about it, because they all have side lengths that are equal. And if I were to multiply the side lengths by a certain number, I'll just get a bigger version of the square. And all circles are similar shapes. But we have there's obviously a lot of other shapes we can draw that are similar shapes. It doesn't necessarily have to be triangles. But yeah, so let's take a look at some of the interesting things we see in similar shapes. So one thing I can do is there's a relationship between this or the corresponding angles. So for example, if I were to take that length, which is 3, and I divided it by 6, which is the corresponding angle, obviously I'll see, well, 3 over 6 is a half, right? But I'll see that is the same as if I were to take this side length, which is 4, and the corresponding side length is 8. So I see that's a half as well. And it's the same with the 5 and the 10. So all of these are equal. So when we have similar shapes, the ratios of corresponding angles are the same and they'll give me the same answer. I could also do the opposite, right? So the inverse would be true if I were to take the big or the longer length over the shorter length, that would be 6 over 3. Or if I took the longer length here, which would be 8 over 4, and the other one, which would be 10 over 5, all of this are equal. Oh, sorry, wrong marker. They're all equal. This would give me a half, and this would give me 2. And you see, well, this what we call this magic number we get, like the scale or the scale factor, because it's the number I have to multiply, divide with to go from the one shape to the other shape. And in this case, you can see, well, there's 2 and a half, and basically the one is just the reciprocal of the other one. And you can look at it like this. If I said 3 times 2 will give me 6, that works. And 6 times 2 will give me 3. But I can also use the half. I'll go, if I said 6 times a half, that would give me 3. And now the tricky one is saying 3 divided by a half would be 6. Now it just says how many halves would go into 3, and that would be 6. So there's a correlation between these sides, and that's not all. There's even more things that we see if we look at similar shapes. If I had to compare, let's say, the internal shapes, if I took the 3 in this shape and I compared it to the 4 in this shape, and I did the same here, I took the 6 in the big shape compared to the 8 in the other shape, I see, well, they are also similar. 3 over 4 is the same as 6 over 8. And consequently, it's the same for 3 over 5 is the same as 6 over 10, or 4 over 5 is the same as 8 over 10, or 10 over 6 is going to be the same as 5 over 3. So there's a correlation between these ratios. So that's one thing we should know, is that similar shapes have this thing we call a scale factor, by which it just grows or shrinks by that number. Now, till now in these examples, we've only worked with, let's say, flat surfaces. So let's take a look at, let's just go to the next bit of information that's kind of important for us. So if I, let's say there's a line, I'll draw a line here, a red line, and we'll do a blue line. And I'm saying the one, let's say this is 5 meters. Obviously not according to scale, and 10 meters. And if I asked you, hey, like I said, let's say these lines or side lengths of similar shapes, I'll draw the rest of the shapes now, but what is happening with the 5 to get to the 10? Well, you'll say, well, I'm just getting, if I wanted to find the relationship, I can take the bigger number, which is, let's say, the 10, and I'll put it over the smaller number, which is 5, and then I'll get 2. And this is what I would call I'm going to call it SF for my scale factor, because 5 times 2, let's make a little multiplication there. Yeah, let's do that. 5 times 2 is 10, and obviously 10, if I'm, let's rather do this. If I'm going, let's say if I'm going that way, I'm going to multiply, because 5 times 2 is 10, and this way I'm going to divide, because 10 divided by 2 is 5. So this is my length scale factor. Now, you must know, or you obviously know, that if I can only add similar like terms together, right? So if I were faced with something like a plus b, it just stays a plus b. I can't have, I can't do anything with that. They're not like terms. In the same way with x, if I can add x plus x, that would be 2x, but I can't add x with x squared. These are not similar or like terms. And in the same way, when I work with length, I have meters here, but let's say if I had a different shape, and now let's draw a little square here. Okay, I promise you that's a square. And another square, which is obviously not according to scale, but this would be the bigger one. And I said, well, this is 5. Oh no, let's just put that marker away. It's not going to help me. 5 meters by 5 meters. And here I have 10 meters by 10 meters. So now I have 2 shapes. They are similar shapes because they're both squares. And I can see that just like there, the 5 doubled to get to 10, the 5 is doubling to get to 10. But if I work this out as an area, this would be 5 times 5 is 25, and m times m is m squared, or square meters. And in the same way here, 10 times 10 will give me 100 square meters. So there's something now. Let's just take a look at this. What's happening here? When I had lengths, I took the length and I multiplied it by 2 and I got 10, and that worked fine. But that's not going to work with that 2 is not going to work with these lengths, because if I take 25 and I multiply it by 2, I'm only getting 100. So there's a different way I should find the scale factor here, and it's exactly the same way. So where for length, let's just write here length, and this is area. So for length, I took the big length over the small length, and I got this 2, which helped me. And for area, I can do the big area over the smaller area, and there I would get 4. So something happened. It means that if I have a shape and they're similar and the lengths increase by a little bit, the area actually increases by more. I can't use the same scale factor. So in this case, length went up by 2, or not by 2, it doubled. It increased by a scale factor of 2, but area went up by a scale factor of 4. Now, this 2 and this 4, you might think, okay, well, doesn't really look very significant, but it's actually a little trick. I can write 4 as 2 squared, right? And now you should be able to see this, that something magical is happening. So my units are squared. So all I do with my scale factor, you can see the scale factor for the lengths were 2. Now the scale factor for the length is just 2 squared. So if I had a length scale factor of, let's say, 3, then this would have been 3 squared. So if I went from 5 to 15, so 5 times 3 is 15, and here I had 5 times 5 is 25, and here 15 times 15 is, I think, 225 or something. Let me just check before I continue. Yeah, 15 times 15 is 225. Then I'll see, well, 25 times 3 squared would give me this. Now we're going to look at examples later, but for now, you should just realize that this scale factor is very important for us. So if I had I'm going to box it in green. So this scale factor and this scale factor, they're very important for us. We can't compare, like, the scale factors, they're similar, but they're not going to be the same for length and area. And then you guessed it, if I go even further and I draw a very beautiful cube here, as you can see. Okay, again, not according to scale. My blue cubes are getting smaller and smaller and smaller. So again, if this was maybe 5 by 5 by 5, I would get 125 cubic meters. And here, if I had 10 by 10 by 10, this would be 1,000 cubic meters. And if I wanted the scale factor here, I can take the 1,000, or the big number, and divide it by the small number, and then I would get 8. And interestingly enough, 8 can be written as 2 to the power of, I'm wondering, there's a 3 there, and there's a 3 there. So I assume 2 to the power of, well, not assume, I know obviously, but 2 to the power of 3 is going to give me 8. So the important thing to realize is that when I have similar shapes, they go up in a certain ratio, and these ratios might have something to do with each other, but they're not going to be the same. So let me just write here volume. Now you might ask yourself, well, what if I put 5 over 10 and 25 over 100 and 125 over 1,000? So I just switch them around. Well, then you'll get a half, a quarter, and an eighth, which is still, I mean, if I write it here, so a half, a quarter, and an eighth, which would still be, a half is the same as 1 over 2 squared, and an eighth is 1 over 2 cubed. So it doesn't really matter. For our examples, I'm always going to put the bigger one over the smaller one, just because it does get confusing later for students if I say, well, you can multiply by the one or divide by the other one. And so I've just realized that, you know, there's kind of, I'm going to teach you it's almost like paint by numbers kind of way, and it kind of always works. But obviously, the more you do these types of questions, you'll be like, okay, but I didn't want to have to put the big number over the small one. I could have multiplied by just the fraction instead of the improper fraction or anything. But one thing that we should know, and this is the knowledge we need for obviously to solve the kind of problems we're going to get in our exam, is let's do a little little block over here, something that you can write down for yourself. So let's say I have the one thing is length. So length is measured in, I'm just going to say here, length can be measured in oh dear, that doesn't look good. Let's do this. We say we can measure it in meters or millimeters or centimeters. You know what? That doesn't look good at all. Sorry. I'll just keep everything nice and neat. So length. There we go. And I'm going to have millimeters, centimeters, meters, kilometers. And when I'm comparing lengths to lengths, then I can use the scale factor I got. I'll just take the big number over the small one, and we'll look at examples later. But I might also get something called area. So let's just write area in a different color. Area. Make it a little bit more colorful. Area, and area is measured in different units. So it would be squared millimeters or millimeters squared or kilometers squared, etc., etc. So these are what we measure with. But if I have a scale factor for length, like the 2 here, it doesn't work for area. I have to do something with it. So it's like a little, let's say it's a little house and this is level 1 and level 2. If I get the length scale factor and I want to compare areas, I'm going to have to take my scale factor and I'm going to have to square it. That makes sense because the 2 squared gives me 4. And similarly, if I were given 2 areas and I could work out the scale factor of area and they asked me some lengths, I can't use this 4 as my scale factor for length. I have to kind of go down a level and I have to get the scale factor square rooted. Now I'm going to write a little 2 there just so that all the 2's look so nice together. And the top part of my building, I'm going to call volume. And these are obviously measured in, let's say, millimeter cubed and centimeters cubed, meter cubed. Obviously, sometimes they do something weird and they write liters. So I'm just putting that in because I have seen that before. But liters is also volume, so it's not always a unit that has a 3 in it. So I'm just putting that there in brackets. But if I have volumes, or I'm comparing volumes with each other, and I'm dividing them, then I get a different scale factor. So this scale factor I can only use for volumes, but if I wanted to go to lengths, or if I have lengths and I want to compare volume, then I have to take that length, and I'm going to have to, where is there some space? So if I were, let's do a different color. Let's do the blue. So if I'm going up to there, I have to take my scale factor and I have to cube it. And the same way, if I'm going down, do I have enough space here? If I'm going down, I'm going to have to cube root my scale factor. Now we'll look at different examples, but the big thing that you should understand is that all scale factors are not equal. All units of measure are not equal. So just like I can't add meters to square meters to cubic meters, whenever I'm comparing similar shapes, I have to make sure that my scale factor fits the unit I'm measuring in. So for length, I can measure all the lengths and compare lengths. If I get a length scale factor and they're asking me to get an area, then I have to square to go up. And if I have length and I have to get to volume, then obviously I have to cube to get up. Now the trickiest one I've seen is that when they give you volume and you have to compare area, and we'll look at that in a different video. There's no way, well, there is a way, but I'm not going to explain that now. There's not really a way that I've shown till now how you can get from volume to area. So the only way to, sorry for that delay. The only way to get from volume to area is by taking my volume scale factor, cube rooting it to get to length, and then I have length, and then I can square it to get to area. Now with the indices rules, you'll see that there's the quicker way to do that. But to go from volume to area or area to volume, that's kind of what you have to do. So for area to volume, you have to square root first, and then you have the length one, and you're going to cube root. Well, sorry, just cube it. So this is the kind of the introduction to similar shapes. This is the info you need. In the next video, we'll look at some examples and some past paper examples of what they will ask you. Yeah.